1105, Lab 5. This lab, you're going to be looking at bends and fittings in a pipe or energy losses associated with bends and fittings in a pipe. So, pipe networks always don't have straight line pipes, so we have to change the direction of the flow. And oftentimes we make use of bends and fittings either to split the flow or change the direction of the flow. Valves are also used sometimes to either divert flow or even regulate flow. And water supply networks typically have pipes of varying dimensions. So if you take a typical water supply pipe network, the larger pipes move water from the treatment plant to the neighborhood, and then smaller pipes are used to move that water into individual households. So similarly, if you look at the wastewater treatment network, we have smaller pipes that move wastewater out of individual households, and they're all connected into a larger pipe or the main trunk line from which water is moved. Excuse me. Water is moved to the wastewater treatment plant. So there are times in where we have vents and fittings, and then there'll be times when, or locations in pipes, when we'll have a sudden expansion in a pipe or a certain contraction in the pipe. So there are always losses associated when there are bends, fittings, or when we have pipes of varying sizes at entrance and exits. So all these losses are called minor losses. They're called minor losses because friction always happens in a pipe, or friction losses always happen in a pipe, but minor losses only happen when there is a bend, fitting, or change in a pipe configuration. As these losses are localized within the network, they are often termed minor losses. But nonetheless, right around that bend, fitting, or even expansion or a contraction of a pipe, there are going to be significant losses that have to be accounted for. So again, these losses add up over the entire network, and then if you have a lot of bends and fittings, they can contribute to a big chunk of energy loss within your system. So minor losses must be properly accounted for during the design of pipe networks. So to study minor losses, our fundamental equation again is the Bernoulli's equation. So I write P upstream. So I'm going to use two locations, upstream and downstream. That is right before this contraction term, or like where you're seeing a change in the pipe diameter. So you have P over gamma upstream plus V squared over 2G, which is the kinetic energy head, and then Zu, which is the potential energy head, is equal to PD over gamma, which is the downstream pressure head, Vd squared over 2G, which is the downstream velocity head, the downstream potential head, and then there is a loss term. Here I'm ignoring the friction loss and I'm just showing you a minor loss term. So these minor loss terms often have to be empirically determined from experimentation. And what we see is that the head loss due to minor losses are proportional to the velocity head. So what I show here is H head loss subscript m is used for minor loss is proportional to V squared over 2G. And I can turn that proportionality to an equality by putting in a loss coefficient K. Okay, so which velocity are we going to use in defining minor losses, especially if the diameter of the pipe changes? It's always the smaller diameter pipe that controls the head loss term. So if you want to calculate the minor losses, we always use the smaller head loss term, or the smaller diameter pipe, or the velocity in the smaller diameter pipe to get our velocity head to calculate our minor loss. So losses around bends. So here I show the three types of bends we'll be looking in our lab today. The meter bend is a very sharp bend, so there is a bend at 90 degrees. The elbow bend is a little bit more, it's also a 90-degree bend, but it kind of does it more gradually. The long radius 90-degree bend is also a 90-degree bend, but it uses, or that transition is over a much larger area, or much larger diameter. So So what's important is that the losses in a bend are proportional to the radius of curvature. The radius of curvature can be found if you have a bend, you draw a straight line, and then you draw a line tangential to that bend, and whatever the perpendicular distance is, that is the radius of curvature. That gives us, and if you measure that distance, that gives us the center line radius or the radius of curvature. And the larger the radius of the curvature, the smoother the flow path, and the smoother the flow path for a given radius, there'll be less head loss and then the lower loss coefficient. So the theoretical K values for meter, elbow, and large radius bends vary anywhere between 1.4 to 1.6 for meter bends, 1.1 to 1.4. There's a little bit more smoothness in the elbow bend, so my loss coefficient has gone down. And then for a large radius bend, it goes down quite a bit because the K is much smaller. So if the upstream and the downstream velocities are the same around the bends, if you have the same pipe diameter, then it doesn't matter which of those pipe diameters you're going to use to calculate your head loss. As I said, there are times when a smaller pipe enters a larger pipe. So there is a sudden expansion of the pipe. So the water is moving through the smaller pipe, and then there is an abrupt change in diameter. And because of that, there is a detachment of the flow line from the wall of the pipe. And this causes vortices and turbulence right at that entrance, and then after a little while the flow line again aligns itself with the larger diameter, the wall of the larger diameter pipe, and starts to flow again. So the head loss due to expansion is proportional to the expansion loss coefficient. And the upstream velocity here is the velocity in the smaller diameter pipe. Again, we also know theoretically that this K value can vary anywhere between 0 to 1, and that the K value is proportional to 1 minus velocity of the downstream square over the velocity of the upstream square. So if the pipe diameter did not change, if both the upstream and the downstream had the same diameter pipe, then VD over VU will be equal to VU. So VD squared over VU squared will be equal to 1, and my head loss coefficient will be 0. There is no minor loss in that case. On the other hand, if my upstream if the downstream velocity is if the expansion happens from a very small diameter pipe to a very large diameter pipe, then essentially my KE value will be equal to 0, and in that case my AU over AD will be equal to 0, and my KE will be equal to 1. So if I have upstream to be very small considered to downstream, then I have a very small pipe coming into a very large pipe, so that causes a lot more turbulence, and my head loss coefficient goes up and theoretically becomes 1. Sudden contraction. The sudden contraction is the opposite case of the sudden expansion. Here we have a larger pipe, water from a larger pipe flowing into water from a smaller pipe. So there is a transition zone in that smaller pipe right at the entrance where you see that there is contraction of the flow, and then again the wall, and then again the flow lines come in contact with the walls of that smaller diameter pipe and start moving again. So the head loss coefficient again is proportional to the smaller diameter pipe, which happens to be the downstream pipe. And we can also calculate that the head loss coefficient is a function of the velocity of the contraction, velocity of that contraction, V sub C, and then the velocity of the downstream pipe. Of course, it's not possible to measure values of A sub C, so Kc has to be empirically determined. And when my upper and the lower diameter pipes are the same, then I will not have my AC term becomes equal to 0. I mean, essentially, I'll have the same upstream velocity and downstream velocity terms, and my Kc becomes 0. On the other hand, if my downstream pipe becomes extremely small, then the flow is almost like going from a very large reservoir through an orifice, and in which case the Kc value is equal to 0.44 from empirical determinations or from experiments in the lab. So our K sub C, which is the minor loss coefficient for contraction, varies between 0 to 0.44. Remember, in the expansion case, we went from 0 to 1. In this case, we go from 0 to 0.44. The experimental setup we have again, we'll be using the hydraulic bench, and we'll be using the minor loss apparatus or the energy loss through pipes and fittings apparatus. So we've got three bends: the meter bend, the elbow bend, and the large radius bend. And we also have a pipe that expands and then a pipe that contracts. So there are so the water flows as the water flows through these pipes. We have manometer tappings right upstream and downstream of each pipe. So the numbers of these manometers right here correspond to the various pipes. So what we do is we have an inflow that comes in this way, flows through the meter band, goes up, flows through the elbow band, loses some energy there, loses some energy here, loses some energy here, and then it goes through enlargement, and then it goes through contraction, and then through the large various band, and then it's flushed out of our system. And the manometer pairs are numbered, and we know which manometers belong to which band, which one is upstream and which one's downstream, as long as we know that the water is moving in that direction. So we use a pair of manometers to get our head loss, and then from that head loss we calculate the loss coefficient. So we need to measure the flow rate and the corresponding manometer readings. We do this for several different flows, and then also make sure that you have the necessary pipe diameters. The internal diameter of the small bore pipe is 22 millimeters. The internal diameter of the larger pipe is 28.4, and then the radius of central line is 14 millimeters for the elbow, and then 50 millimeters for the large radius bend. So this information, in conjunction with the manometer readings and the flow rates, will give you all the information that you need to kind of make the calculations that are part of your lab report. And then you'll be calculating your head loss coefficients, and then by plotting the velocity head on the x-axis and the head loss and the velocity head, and then trying to get the intercept or the slope, I'm sorry, of that curve, which will give you the head loss coefficient. Again, the head loss coefficients that you get, you're going to compare it to the theoretical head loss coefficients that I talked about in this lecture, and then see how well your experimental data matches the theory. So, so that's in a nutshell what we'll be doing in the lab. By the end of this lab, you should know what minor losses are and how are they different from friction losses in a pipe. Why are minor losses important for civil engineers? And why do losses happen when there is sudden expansion or contraction in a pipe? Obviously, vortex formation, turbulence. What does the head loss of bends and fittings depend on? This depends on the radius of the curvature and the diameter of the pipe, or the ratio of the radius of curvature to the diameter of the pipe. Why the head loss is proportional to the velocity in the smaller diameter pipe, because that is the velocity, that is the critical velocity, or it gives us the smaller diameter, gives us the larger velocity, which is the controlling velocity. And what is a head loss coefficient? What are the typical head loss coefficients for various bends, fittings, expansion and contraction? So the lab's pretty straightforward. We take a set of manometer readings, flow rates, and calculate the head loss coefficients. Thank you.